So this is the table of content of today's lecture. First of all, we will discuss about the image processing. Then we will discuss some fundamentals related to digital image. And after that, we will see how image is acquired. And we also discuss related to the image enhancement techniques and some modalities of medical imaging and also medical image analysis, and at the end we will discuss some applications related to medical imaging and also some future directions related to medical imaging. So first of all, coming to the image processing. What is image processing? Actually, image processing is a manipulation of images using mathematical operations. Why we use mathematical operations? In order to enhance or in order to improve the quality of the image, so that we can use the information later for our own objectives. For example, in case of if we have some images, in case of machine learning, we need some pre-processing of the data so that we can use the data for the training of the model. And also, for example, in medical field, the pathologist or the radiologist cannot see or visualize those tumor area or the fracture area in the image. In order to enhance the image and to get the useful information from the image, we use medical image processing. So the process of converting an image into digital form and performing some operations on it to get an enhanced image or extract some useful information. So the main objective of image processing is to get useful information from the data, from the image. And for this, first of all, we will convert the image into digital form, and after converting it into digital form, we apply some operations, mathematical operations. There are different kind of mathematical operations to enhance the quality of image. We will discuss in later slides, and in that way we use for further processing. So why it is important? To enhance visual perception or appearance for human interpretation. For example, if you can see here in this image, this is blur image or it is not so good, and there is no any good interpretation of this. If you present this image to someone, he cannot recognize what is inside this image, only some black area and some white area. But after applying some mathematical operation on this image, there are some, we can get some visualization of this image. For example, here you can see the ribs can be visualized here while enhancing and while applying different kind of mathematical operations on this image. So enhance visual perception on or appearance for human interpretation. In medical field, we use these kind of techniques for the pathologist and for the radiologist and for the physicians, so that they can identify the tumor area or the affected area in the body part, and also prepare images for measurement or machine interpretation. As I mentioned before, that we normally we use pre-processing of the data, right? In pre-processing, we use these kind of techniques to enhance the quality of the data, and so that at the end of the process, when we are using for the model training, we can out of form result. And also automate decision making process and enables advanced analysis in fields like medicine, robotics, and security. So digital image fundamentals. Actually, image is a two-dimensional visual representation made up of tiny squares called pixels. This is an image, for example, and these are the pixels. Pixels are the building block of image. These are different pixels, and it has some values. For example, 0, maybe 1 to 6, depends upon type of image. If it is binary image, then you have 0 and 1, and if it is grayscale image, then there are different ranges of pixel values. These are pixel values, maybe 250, 176. So these are the pixels. These are called the pixels, and each pixel holds a numerical value. So each pixel has some values. So these are called pixels, and pixels have some values. And key feature of digital images. Basic, as I mentioned, this is the basic building block of your image, and image resolution is the size of image, maybe 256 into 256. This is the resolution of an image. Means you have an image of 256 width and 256 height. And the formats are different kind of formats: JPEG, PNG, BMP, TIF, DICOM, SVS, and these kind of different kind of formats of medical imaging. So type of image, digital images. We have basically three kinds of digital images: binary image, grayscale image, and color images. In binary images, here you can see we have black and white. Black represents 0 and white represents 251 in this case. But here we have grayscale images. It has different ranges of the pixel values. For example, if it is black, it means it has 0 value, but it is a little bit gray, then it has different value, ranging from 0 to 256. Likewise, we have color images. In color images, we have 3 channels: red, green, and blue channels, and we have to deal these different kind of images accordingly. So coming to the binary image, as I mentioned before, that binary images has only 2 values, 1 or 0. For example, if it is 1, it means that it is white area. For example, here in this case, these are the value is between 1 and 0. 0 shows the black area. So binary images has only two values, 0 and 1. Mostly it is used in document scanning and optical character recognition, object segmentation in computer vision tasks, and we set some threshold values for this, how to differentiate between 0 and 1. Maybe we set some values. For example, if it falls in that range, we say that it is 0, and if falls in another range, then we say that it is 1. So actually it differentiates between the foreground and the background. So then we have grayscale images. In grayscale images, it has 8 bits per pixels, and it varies. For example, pixel represents varied levels of gray, typically ranging from 0 black and 255 there is white. Here you can see this is a pixel. From this whole image we take a pixel, and it has, for example, multiple pixels maybe. So it has different ranges. Here maybe it is 230, maybe some other area it has 229. So it means that there are different pixel values of the image in grayscale images, but in binary images we have only 2 values. It is mostly the application of grayscale images are in X-ray images, CT scans, in order to differentiate the fracture area in your body, or to find the tumor area in any part of the body, and also black and white photography and image processing task where color information is unnecessary. where we don't want to focus on the color of the image, we just can use this grayscale so that it help computationally. For example, if we deal with color images, then it needs, the processing time will be more, and also it needs high computational resources. So then coming to color images, this is a little bit advanced form of the image in which we have 3 channels. In the previous we have only 1 channel, but here we have RGB channels, 1, 2, 3, so 3 channels. We also consider the for example, when we are performing some operation on the image, we use the channel values as well. For example, we consider 256. For example, we have a size of 256 by 256 image. Then we also use the channel values also. Then we multiply these and we calculate the total pixel values, and we perform operation on the image. So it is a little bit heavier than the previous ones. The application of these color images are digital photography and videography, color printing and publishing, and mostly it is also used in functional MRI visualization. So here you can see the different pixel values. For example, RGB are red, green and blue. It has different pixel values, and these are overlapped, and you have to calculate the total pixel values of the image. Image representation. So how can we represent the image? If we take this example, it starts from here. For example, 0, 0. It has, this is Y and this is X. Your Y shows, for example, number of rows shows the height of the image, and number of columns shows the width of your image. And this is for grayscale image. For example, this area, the pixel value for this area is, for example, 235, and the pixel value for this area, it is a little bit gray, and this is white, and this is gray, so they have different values. And likewise, for this pixel, it has 3 channels, as I mentioned. It has different values, RGB channels. So maybe red channel has 49 value, green channel has 61, and blue has 152. So there are different values for each channel. I have explained these things. And how can we represent the images? 2D image, M into N, where M is the number of rows, for example, number of rows, and M is the number of rows, this, okay. M is the number of rows, height, which is showing the height, and N is the number of width, showing the column. Same goes for the RGB image, and here we are including the channel value as well, and all the things will be same. So basic steps involved in digital image processing. These are the basic steps. First of all, we have to acquire the image, we have to get the image. Then if there is a problem with the data, then we have to apply some enhancement techniques to increase the quality of image, that is image enhancement. Then also image restoration is also a kind of image processing, in which if there are some part of the image is missing, we apply different operations and we restore that area of the image. And color image processing, wavelet and image transform, segmentation, feature extraction, and image patterns and representation. So first of all, image acquisition. In image acquisition, there are certain things we have to consider. We have energy source, That may be sunlight or X-ray or ultrasound. And we have the object. Maybe in case of medical imaging, we need to take the image of different parts of the body, maybe chest X-ray or fracture in the bone. So that is the object, and some equipments which has sensors, and those sensors are used to capture the image using the illumination. This is actually illumination and source of energy, and we will discuss detail in the next slides. So here, this is the typical example of image acquisition you will find in most of the books. Illumination source may be sunlight, maybe X-ray, ultrasound or scanner, and this is the object. Object may be the body tissue or a body part, and this is the imaging system which has CCT and CMOS. These are different kind of chips, and this is slower but gives some clear information about the image, and this is the advanced form of chip, and this is mostly used in your cameras, CMOS. First, there must be a light source is required. Without light, for example, if we take normal picture, if it is in dark, the object is in dark, then we cannot get a clear picture of that image. So illumination source is important, whether in medical or in real applications as well. So then we have object, and after that, using this device, we capture the image with the help of this rays, illumination source, and we digitize the image, and in this form, and you get the pixel of the image. Actually, we are digitizing the object. These are the things I have already explained. For example, the process begins with an energy source, typically light, invisible imaging, X-rays. For example, if it is X-ray imaging, then in radiology, X-ray will be used. And ultrasound imaging, we use some ultrasound waves. And for example, in digital pathology, we use different kind of scanners. And seen elements are your physical object, maybe your chest, maybe your tissue, maybe your bones. And imaging systems are the scanners, or the imaging system captures the energy that has interact with the object. Is here, you can see. Then internal image plane. This is a conceptual layer where the optical or physical objection of the scene occurs. The system uses lenses and filters to focus the image onto the sensor surface. So at the end, we get the digitized image. So why image acquisition is important? Because this is the very first step in image processing. If you get a quality image, then after that you can perform better results at the end. For example, if your image is not so good, then how the doctors or the radiologists can observe the affected part in the image. So this is very important. Your image source and your image illumination and the image equipment should be of good quality, so that you can capture high quality image, and the useful information can be captured from the image. So poor acquisition can lead to misinterpretation affecting outcomes. Definitely, if the quality of the image is not good, then the model, for example, if you are using for some deep learning or machine learning, then the output will also be overfitting, and it will interpret false results. And likewise, if the image quality is not good, and if any physician is looking at your X-ray, he or she may interpret wrongly, and that will be a disaster. So factors affecting image quality. Here are different factors. You can see illumination. Illumination is also important. The intensity and the direction of the light source. There must be a proper direction of the light source, and your object should be in that position so that maximum light can focus on the object and you can get high quality image. And likewise noise, random variations in brightness or color can obscure important details. So you should also focus on this noise reduction, and one should remove the noises from the data. Likewise, it also depends upon the sensor characteristics, because resolution also matters, sensitivity also matters, and dynamic range also matters. Likewise, optical properties and the motion. For example, if you are taking the image with motion, then you cannot capture the image with high quality. So in movies, maybe you have observed that they tries to minimize the motion while using different kind of techniques. So image enhancement. Image enhancement refers to the process of improving the visual quality of an image or making certain feature more visible or prominent without altering the original content. Here in this image you can see that we have an image. This is blur image, and we cannot identify very clearly that what is inside this. But after applying some operations on this image, we can now in this image we can say that there is a man with black long coat, and he has some camera, and it has stains, and the color of this is white and black. So we can identify, and we can interpret more information related to the image on the right side. So increasing contrast and visibility of texture edges, and reduce noise and artifacts, highlighting specific anatomical structures, improving diagnostic accuracy. So here you can see that we have increased the image quality, and there is a contrast. For example, we have increased the brightness and contrast of the image. You can see on the right side. So the applications are in medical imaging, highlights tumor or tissue contrast. Likewise, in remote sensing, improving satellite image clarity. In industries, find the anomalies in the products. And in photography, brighten or sharpen underexposed images. So these are different categories of image enhancement techniques. There are different techniques, for example, spatial domain, histogram-based techniques, frequency domain, and homomorphic filtering. So these are the techniques mostly people use to enhance the quality of the image. So in spatial domain techniques, mostly people use contrast stretching, image smoothing, for example, mean, median, and filtering. Actually, it is the operations on the pixel values. Taking the pixels, we apply different techniques, and for example, in mean, for example, we take the mean of this and we apply this mean to these 2 pixels. Likewise, mean filtering and median filtering and Kenny, and for edge enhancement, we use mostly Kenny, Laplacian, and Sobel, and other techniques as well. Likewise, histogram-based techniques also we use, which is used to modify the distribution of pixel intensities, automatically improve contrast and brightness. And key techniques in this histogram technique, we have histogram equalization and adaptive histogram equalization. So here in this case, you can see that this is a little bit blur image, and the histogram of this is like this. But here it has been increased and applied different kind of operations, and the quality of image has been increased, and you can see the histogram like this. So in frequency domain technique, we have low pass filters, that is smoothing, high pass filter, sharpening, and band pass filters, edge enhancement. So what are the advantage of these? Useful for global pattern analysis, noise reduction, and deblurring. Challenges are requires more computational effort, interpretation of frequency domain may be less intuitive. Then coming to the medical image modalities. Most of you have experience of working with different kind of modalities. There are different kind of modalities in medical imaging which are used to visualize the inside of the human body for diagnostic, monitoring, or treatment purposes. For example, in X-ray images, mostly in pneumonia case or in COVID, during the COVID-19, mostly people used to have X-ray images and find the affected area in the lungs. And also we have X-ray, and we have CT, and we have MRI images, and PET images, and ultrasound images. So these are different kind of modalities in medical imaging, and people are using these techniques for image acquisition. So coming to X-ray image, this is the oldest form of medical imaging, and it was discovered in 1895, and it used ionization radiation that passes through the body, and dense tissue bones absorb more radiation, appearing white. Here you can see that the flesh is not visible here, only the bone areas are mentioned here, shown by these X-ray images. And less dense visual examples are skeletal imaging, chest X-rays, and mammography. And applications are detecting fracture, infections, and tumor. For example, bone fracture, we use X-ray imaging, and for pneumonia or COVID kind of things, we use X-ray imaging. And computed tomography, this is a little bit advanced form of X-ray images. In X-ray images, we take images from one angle, but here in this case, the images are taken from multiple angles. For example, use multiple X-ray measurements from different angles and compute processing images to create cross-sectional views. From here you can see there are different images are taken from different angles with this equipment, and you have a cross-sectional of your image so that it can provide better information related to your body part. The application is diagnosing vascular disease, muscle and bone disorders, detecting internal injuries and bleeding, trauma, and cancer. This is another kind of modality, magnetic resonance imaging, and uses strong magnetic fields and radio waves to generate detailed image of organs and tissues in the body. So multiple acquisition sequences, it has T1, T2, and flare. Mostly it is used for brain related disorders. And MRI sequence, for example, T1 weighted, it fluid appears dark, fat appears bright, used for anatomical or structural detailing. So here you can see about this T1 weighted, and this is an example of T2 weighted, and this is flare related to highlight abnormal tissues in the brain. So these are different functionalities of MRI. And this is related to positron emission tomography. It is nuclear medicine imaging techniques, as it uses radioactive substances, uses radioactive traces which are injected into the body, and scanner detects positron gamma rays emitted by tracers to measure the metabolic activity or biochemical function of the body. So based on this image, they use positron, which is actually a gamma rays. In X-ray images we use X-ray, but here they are using gamma rays. Then we have ultrasound imaging. Uses high frequency sound waves that reflects off body structures, real-time imaging capability, and relatively it is inexpensive and portable. I think Kiramat is working on ultrasound imaging, right? Yeah. So there are different modalities we can use for different purpose. Then importance of medical image analysis: early detection and accurate diagnosis, treatment planning, response assessment, and research. So in early detection, we can identify while using these kind of images and apply machine learning and deep learning, and we can early detect that the disease can appear or the patient may fall off this kind of disease or not. So there are different applications of medical imaging. Then challenges: volume, thousands of images generated per examination; complexity, variability, integration, and interpretation. For example, in real-time applications, we have so many patients coming to the medical institutions. So for every patient, they are generating so many images, and to deal with those images is very challenging. And for that purpose, we have to automate such kind of systems while using the latest techniques, for example, machine learning or deep learning techniques, so that we can overcome these kind of volume, complexity, and variability while integrating and while considering all these kind of, for example, if you are taking image from one patient and there is another patient also coming, then if you combine the data taken from all those kind of different kind of patients, and if you train your model, then your model's generalizability will increase. Otherwise it will underperform your overfitting. It will show the overfitting. So these are the challenges. And the application, AI applications in medical imaging. You are all very familiar with these kind of techniques. For example, we use AI for detection, segmentation, classification, quantification, and prediction. In detection, we use, for example, AI techniques for tumor detection and the affected part in the images and fracture part in the bones. Likewise, segmentation to segment out different parts of your images. For example, you want to segment the tumor area and the normal area. We use segmentation and classification. For example, it is whether it is normal or benign or malignant. So we use for classification as well, and other applications you can see here. And application of image processing in medical imaging we can use for remote sensing and agriculture we can use, and for industrial automation we can use, and for law enforcement and security. So these are the different applications of image processing. Then we have different kind of AI techniques in medical imaging. This is the basic. For example, CNN is the basic, very basic approach we use for different kind of tasks. For example, detection, segmentation, classification, quantification, and the prediction. And likewise, UNet architecture, mostly it is used for image segmentation, and generative adversarial network. These are used for generating new images from the existing images. And nowadays it is also very popular, generative AI and diffusion models and transfer learning, in which we have different kind of architectures. For example, ResNet, VGG16, MobileNet, and Inception. So many other techniques. Most of you already know these kind of techniques. And ensemble methods. In ensemble method, what we do, we combine different kind of approaches together to enhance the performance of the model. For example, if we combine VGG16 with ResNet, or any other kind of, for example, 1D CNN with some other techniques. So these kind of things are ensemble methods. Then we have weakly supervised learning. In weakly supervised learning, we have incomplete or inexact or indirect labels. We have to deal with such kind, because in medical imaging, to annotate or to label the huge amount of data is very time consuming and also laborious. So in order to overcome these kind of challenges, people are coming up with the idea of weakly supervised learning technique. And with this technique only we need inaccurate level. For example, in case of if I talk about digital pathology, we have a slide. For example, this is a slide, whole slide images. What actually we are doing, for example, we are applying weakly supervised learning technique for whole slide image classification or detection of tumor in whole slide imaging. So we only need, although this area is tumor area in this whole tissue, we only use weakly label. Weakly label means we only use, for example, for this label, for this whole slide, maybe we use some label. Based on this label, we can identify which area in this whole slide, this area, we can identify this area is the affected area, for example, tumor area. This is the power of weakly supervised learning, in which we use multiple instance learning. For example, we have different kind of bakes. We consider in MIL, we consider a WSI as a bake. Bake means if the WSI has a tumor area, then it is called positive bake. Positive bake. And if any bake doesn't contain any kind of for example, tumor area, then we will say that this is negative bake. So there is a concept of positive and negative bake in multiple instance learning. We apply these kind of techniques to identify the tumor area in the whole slide images. And the another technique is self-supervised learning. Here in weakly supervised, we need a kind of label, weak labels, but in self-supervised learning, we don't need any kind of label. For example, we just give this whole slide image to the model, and it can identify the tumor area in the whole slide. This is the power of self-supervised learning technique. And there are different kind of self-supervised learning approaches people are using, and it doesn't need any kind of label or ROI annotation. And the future direction in medical imaging, federated learning. This is a new concept particularly in digital pathology, where the models are trained at different nodes, and they just send the weight of the model to the central network, and from there it can send the output to the nodes. So this is the basic concept of federated learning, and it is also very popular in digital pathology. And multimodal integration. In multimodal integration, we have, for example, different kind of modalities: X-ray images, CT scan images, even text images, structured data or unstructured data, and also omic data that is related to DNA and RNA. So these are different kind of modalities, and people are now moving towards the multimodal integration, taking different kind of data and making single unified model. And it can, any kind of data you can give to the model, and it can interpret, and it can detect the disease while using those kind of data. So explainable AI, in explainable AI, for example, I have mentioned that here the model can explain why the model is predicting this area as a tumor. So this is also very important in AI nowadays, and people are focusing on explainable AI, moving towards explainable AI, and which shows the transparency of your model, that, and it gives the answer that why the model is predicting like this, what are the factors that affects and that force the model to predict this area as a tumor or normal. And radiomics also extracting quantitative features from medical images. There are some deep features as well. For example, while using CNN and other kind of architectures, we are extracting the deep features of the image. But while using radiomic features, for example, GLCM and other kind of radiomics we use, those are the texture features, kind of superficial features from the images. And if we combine those radiomic features and as well as the deep features extracted while using the CNN architecture or other kind of transfer learning architectures, then the model's accuracy will enhance. And we have digital twins, and at the end automated reporting. Nowadays there is a concept of VLMs, vision language models, in which you will give the image as well, and also it generates the report as well. It will, for example, in this example, for example, this is a whole slide image, and it will tell that the type of this tumor, and also give the detailed information related to this tumor, why it is tumor, how it is serious, and the stages, and different information related to this tumor area, or if it is normal, then why it is normal. It also generates the result just like the physician or doctor or pathologist or radiologist. So these kind of things are nowadays in medical imaging and AI.